We are taping, apparently. Yes. Alrighty then.
Yeah, it's a remote 45 favorites. Yes. I don't know what its range is though, so I just turned one down. All right. Alrighty then. So I'm going to attempt to see how far I can get without cough drops. I feel a little less coffee today. I shouldn't have said that because I probably just doomed myself. I know. I taunted it. That was stupid.
Yeah, you're choked now though.
Yeah, man. I just deserve whatever I get for that. All right. So, you know, if I have a cute little patch of surface charge, so this has sigma on it there, you know, some little patch, local sigma charge density there, then we would expect the force per unit area, so that's what this is, force per unit area, force per unit area, that's why we're writing it as a little f, should be sigma E, we would think, but the question is, what E exactly? Because at a surface charge, there's a discontinuity, right? The electric field jumps at the location of a surface charge by an amount sigma over epsilon naught. So should we use E on the top? Should we use E on the bottom? Well, that couldn't be right because top and bottom are completely arbitrary. What E should we use? Well, if you made a guess, you'd probably think, well, maybe the average of the top and the bottom. And that would be correct. In fact, it should be the average of E on top and bottom, or one side and the other, however you want to put it. And the justification for that is similar to what we were talking about last time with conductors and surface charges, and the field at the conductor is both due locally to the patch and due to the rest of the conductor. But here we'll say something more general. I mean, even if we're talking about an insulator, this is just in general for some surface charge. What is the force per unit area on that surface charge? Well, can something exert a force on itself? A net force on itself? No, right? Because there's a great man of physics who produced some laws, and one of which was Newton's third law, right, that said forces come in pairs, and if object A exerts a force on object B, then object B exerts an equal and opposite force on object A, which means, for example, if you're in outer space, you know, you can flail along, flail your arms all you like, you're not going to be able to move your center of mass or accelerate your center of mass, because any force that part of your body exerts on another part of your body, well, that other part of your body exerts an equal and opposite force on the first part, and so the forces that you exert on yourself cancel in pairs, and you can't exert a net force on yourself. And that certainly applies to our little patch. The patch can't exert a force on itself. The only force it could be feeling would be the force due to the electric field of the rest of the system, be that a conductor, be that an insulator, be that a Pop-Tart, you know, whatever you like. I guess a Pop-Tart is probably an insulator, but then the foil wrapper is probably a conductor, so it's an interesting electric, never mind. What we do here is we say, all right, well, let's figure out what the electric field due to the rest of the system is, E other, if you will. So we'll say, okay, here's a zoom in on our little patch with charge density sigma, and so we know that due to the patch itself, if you get close enough to it, it looks like an infinite plane, and tasty there, or is that?
Battery acid.
Battery acid, yeah. You look like you're drinking battery acid there with that expression. Wow, nice. That's the expression I get when I'm drinking cough syrup. Well, I don't just chug it. Right. Yeah. That's right. Damn, I wasn't supposed to let that out. Yeah. So here's our little patch. Let's let the hat be pointing up there. And we know that right above the patch, the electric field E above, due to the patch by itself, that's what the sub-patch means there, is sigma over 2 epsilon naught times m hat. And then below it, infinite plane again, it looks like if you're close enough. Let me only need my Yes. Infinite plane means it'll be pointing down, sigma over 2 epsilon naught in the other direction there. So E patch below, you're probably thinking, well, you know, if you didn't do a lot of homework, I wouldn't need to yawn.
Until 3:30.
If, yeah, I know, yeah,
That's
so,
serious.
that's right, yes, No, still, this is too much excitement, I don't care how tired you are, I know we all
I was still thinking about us processing. But I
You were
was
processing?
outwardly
Okay.
yawning.
Yeah, well, you know, some people have hypothesized that you yawn in order to get more oxygen to your brain, so maybe you were just trying to do exactly that in order to better process.
I agree with that.
Yes, okay, let's go with that then. All right, so then below, minus sigma over 2 epsilon naught n hat, and then we'll say, okay, and then whatever, here's the electric field due to all the other charges in the system, E sub other. Who knows which way it really points, okay? So then we could say then that the total electric field above is going to be the electric field due to the patch plus the electric field due to the rest of the charges in the system. Whoops, what am I looking at? E patch. Let's see, okay, well, funny use of subscripts and superscripts, huh? Right. Okay, never mind. I'll just put in the, so E above is equal to, E other is what I really meant to say here, silly Dr. Harmon, plus sigma over 2 epsilon naught n hat, whereas E below will be E other, which is continuous across the boundary, right? Because, remember, same argument as last time, the E other is due to all the other charges in the system, so there's no contribution from the patch itself, so as far as it's concerned, there's no reason to have a discontinuity there. So E below be E due to the rest of the charges in the system, and then minus sigma over 2 epsilon naught n hat, contribution due to the patch itself. So then you just add them up, and you find that E other is equal to 1/2 of E above plus E below. Right? When you add them up, you get E above plus E below is 2E other, because the patch contributions cancel when you add them up. So therefore, solving for E other is just half of E above plus E below, or in other words, well, I look at that, it is the average value of the electric field above and below the little patch. And so sigma, so the force per unit area should be the charge per unit area times E other, because the patch can't exert a force on itself. It can only feel a force, a net force, due to the other charges in the system, and they produce E other. F is sigma E other, or in other words, it's equal to sigma E average. You can find the field due to all the other charges in the system by just averaging the electric field immediately above and immediately below the little surface patch. So, and at first, slightly surprising result, but if you think about it, it yields the requisite happiness and joy, kind of makes sense. Well, it ought to just be the average. There's a jump there. And ultimately, it's because the patch can only feel force due to the rest of the system. Okay, questions, comments, observations, happiness and joy, or a lack thereof? Should the eyes looking back and forth? Yeah. All right. And if we look at a conductor, remember that for a conductor, the electric field is normal to the surface and has magnitude, one way, right? The magnitude is sigma over epsilon naught n hat. So in other words, if the charge is positive, the electric field points out of the surface, because n hat points out of the surface. If the charge density is negative, it points into the surface. And so the average value of the electric field in the case of a conductor is going to just be equal to sigma over 2 epsilon naught n hat, because I'm just averaging 0 and sigma over epsilon naught n hat, so that averages to sigma over 2 epsilon naught n hat for the electric field averaged on the conductor surface. And so that says that on a conductor, the force per unit area is going to be sigma times E average is going to be sigma squared over 2 epsilon naught times n hat. Or, another way to write that is epsilon naught E squared over 2 times n hat, just putting it in terms of the electric field, sigma over epsilon naught at the surface of the conductor. And so that is telling us that there is an outwards force on a conductor. The charge on the surface of a conductor feels an outwards force on it. Because notice, since it's sigma squared, if sigma is positive or negative, this is going to be in the n hat direction. It's going to be an outwards force. And that makes sense from the standpoint of, here's my positive charge, and there's an electric field outwards in that vicinity. That would be tending to pull the charge out, making it want to leave the surface. If this were a negative charge, the electric field would be pointing inwards. So if I have an electric field pointing this way on a negative charge, which way is the force on that negative charge? Other way, right? The electric field points in the direction of the force on a positive charge, or opposite to the direction of the force on a negative charge, because F is QE, so if Q is negative, the force is opposite the direction of E. So whether you've got positive or negative surface charge, there's an outwards force on it. It's trying to get off the conductor. So there's always an outwards pressure then on any surface charge on a conductor that tends to draw the surface charge. It would try to draw the surface charge, off the surface of the conductor. Now, if the electric field is strong enough, it'll succeed. If you exceed the breakdown voltage, it'll actually be able to jump off the conductor and you'll get a spark. But if the electric field isn't too large, then the surface charge will just sit there saying, let me out of here, let me out of here. But it's like me trying to get through this, it's still stuck on the surface, even though it's got a force upwards on it. What's that? Okay, questions? Yes, no, maybe so. I just can't tell if it made sense or not.
We should all go.
Blank stare, that's right. No, you don't have to encourage that because it's already there.
We should just all.
Yeah, just like
Stare.
like this. Okay, anybody? Very good, Nick. That's excellent. Very nice. What's that?
Chad's got
Yeah.
that stare down.
Hey, that's pretty good there, Chad. Yeah. Wow. You only got one eye open too. That's weird. Yeah, that's pretty good too. That's a good puppy dog expression you got. So can I continue? Did this make sense or not? Steph, did that make sense or not?
I think of it.
No, that would be a no.
Sure.
Sure.
You do that, that means you're good.
All right, there's something not making sense here. I can just somehow tell and nobody wants to say it. Is that true? Right?
I don't think so.
Yes.
I don't really understand what's going on.
Okay, thank you, Doug. I appreciate that. This is what I'm looking for. Finally, somebody has the guts to say it. Yes.
Since last class.
I'm not gonna lie, I don't understand last class
It's sigma over 2 epsilon naught, and we just, I was asking
Get it.
questions. It required like 30 minutes of class to be replayed, so we just didn't do it.
Yeah.
But we didn't understand all that.
Wait, you're saying this is back last time?
Yes.
This is last
We're
time.
continuing what we did last time, right?
Okay,
This is
well,
reusing
yeah.
it again.
All
It
right,
must
so
be.
let us review.
It must be.
All right. Where to begin? Okay. A vector is a quantity which has both magnitude and direction. Right.
Who is this Newton?
Captain Newton. Yes. I should know this name. Right. Okay, let's see. Where do I begin? So, everybody buy into the idea that if I had an infinite plane with surface charge sigma on that infinite plane, it would produce an electric field sigma over 2 epsilon naught up everywhere in space, above it, sigma over 2 epsilon naught down everywhere in space, below it. Happy or not? You're not happy with that. Is that true? Okay. All right. Okay. Here is an infinite plane of which I've only drawn a portion. Okay? And I want to find the electric field to this infinite plane. I could integrate, but that would be silly because it's nice and symmetrical. And so instead, I'm going to use Gauss's law. We are, after all, people that like Gauss. And so, so we would draw a little Gaussian cylinder, and we would make it equidistant. The faces, so this is supposed to be the face, the lids of this soup can are parallel to the plane, even though that may not be obvious in my drawing. So, if here's the infinite plane of charge, I've got a soup can, lid here, lid down here, and we make them equidistant on both sides from the plane because we want to be able to claim the electric field is the same on both surfaces. When we're done, we're going to say, well, that wasn't necessary, but when you're making the argument, you can't do that. All right? So, if this has got positive charge density sigma, sigma could be negative, let's assume it's positive. By symmetry, if there's this infinite plane of charge and I'm at this location, which way is the electric field pointing? Straight up, right? What's that? Yeah, if it's positive, yeah. We're assuming it's positive. If it's negative, all right, all right. So, and if I'm below the plane, it points downwards, right? So, up, down, right? Okay? So, on this surface, E looks like that, N hat looks like that. Does E vary from point to point on that surface? No, because the plane looks the same no matter where you're hovering above it. Now, on this surface, N hat is downward, E is downward. On the label side, where's N hat? At this point right here, I draw N hat being like that, right? And E would be then perpendicular to it, so there's no flux through the label, there's only flux through the lids. Okay, if the area of the lid is A, then the flux through the lid, top lid, is equal to yay, yes, yay! And the flux through the bottom lid is? No. The flux through the bottom lid is, because E and N hat are pointing in the same direction again on the bottom lid too. So it's EA again. So EA plus EA is 2. Yay is the flux. And that's equal to the charge enclosed over epsilon naught. The charge enclosed would be sigma A, right? Sigma, because it's intersecting. It's intersecting an area A, charge density sigma, sigma A over epsilon naught. Okay, quick, lightning fast, solve for E.
Sigma?
Yes, YE is equal to sigma over 2 epsilon naught. So an infinite plane of charge produces a field sigma over 2 epsilon naught, and there's absolutely, notice that we said nothing about how far above or below the surface we are, so it's actually constant in space. It doesn't matter where you are, for an infinite plane of charge, if you're above it, if it's positive, the field points away from the plane no matter where you are with magnitude sigma over 2 epsilon naught.
What if you're in everywhere?
And it's still sigma over 2 epsilon naught.
I don't really understand that, because isn't physics always growing?
No. The idea, I mean, roughly speaking, what you can say is that most of the field that you feel comes from the surface charge, say in a cone that's like, like this. Because the charge very far away only makes a small contribution. So, just pretend most of the field's coming in from this cone, right? All right, well, if I get further away from the plane, that cone intersects more charge, right? And so what happens is that as I get further and further away, the field due to any little chunk of charge goes off like 1 over r squared, right? However, as I get further and further away, the amount of area that that cone of good contribution is intercepting is also going like r squared. Because it's a solid angle that I'm sweeping out there, and the amount of area that that solid angle picks off is proportional to the radius squared of a sphere that I draw centered on myself down in the plane. So in a sense, what's happening is, as you get further and further away from the plane, more and more charge is what's contributing significantly to the field that you're feeling, and it just cancels out, so that in the end, it's just a constant field. Another way to look at it is though, even though obviously the charge is not seeing anything, notice that the infinite plane looks literally exactly the same. If you had a perfectly featureless infinite plane, there would be no way to tell just by looking at it how far away from it you are. Because no matter how far away from it you are, you just see this plane stretching off in every direction and look exactly the same. So that makes it at least plausible that no matter how far I am from the charge, I get exactly the same field because it looks the same to me. That's a very rough argument. It's not really legitimate, but you know, because it's charges don't determine the field by looking around, you know, but still, you know, at least that there's a certain plausibility to it. So, and you can prove it by integrating too. You know, you can just integrate over the, you know, the plane, and you find just get exactly the same thing no matter what. Okay, so infinite plane of charge, sigma over 2 epsilon naught, both directions. Now, on a conductor, the idea is that, okay, here's a conductor, and if it's got some charge density distributed over its surface, well, it can't be the same as this situation. It can't be sigma over 2 epsilon naught out and sigma over 2 epsilon naught in. Why not? Because what? No, well, no electric field inside the conductor, right? It can't be right that there's that this would be true because the electric field is 0 inside the conductor. And instead what happens is at a conductor surface, the electric field is 0 inside, and towards the outside, at the outside, the electric field is sigma over epsilon naught instead of 2 epsilon naught n hat. The jump is the same. You're still jumping by sigma over epsilon naught, because if I subtract above minus below here, I get sigma over 2 epsilon naught minus sigma over 2 epsilon naught is sigma over epsilon naught. So the jump is the same. So, question?
Are you saying it's really close to the...
Yeah, really close to the surface. Yeah, arbitrary. This is one of these, you know, as you get closer and closer to the surface, it approaches that limit. And then at the surface itself, it's really undefined because you've got a discontinuity there. And so, you know, if you plotted it, it'd be, and then what do you call in the, well, you'd probably just say, okay, let's split the difference. And that's what our argument was, that when you're asking what's the field, that the force that the charge itself feels, is you split the difference between the inside field and the outside field. And that's what the force on a unit, on a per unit area is on the charge density sigma. Now we can interpret this by saying, all right, no matter, bless you, no matter what, okay, for any charge, for any surface charge, if I get close enough to the surface and I'm not at a corner point, like, you know, the apex of an ice cream cone or the edge of a cube or something like that, as long as you're not at a corner point like that, one of those funky kind of pointy things on the surface, if you get close enough to any surface, it looks flat to you, and in fact, it'll look like an infinite plane. So, for example, you know, compare your view of Earth to the view you'd have if Earth were flat. How do they differ from one another?
Earth's not flat.
Yeah, Earth's not flat, but
I can't comprehend.
right. Right, yeah, giant billiard ball Earth, perfectly smooth Earth, you're standing on this sphere versus infinite flat plane. Do they look significantly different to you? No. If you fly far enough off the surface, sure, you can tell Earth is round. But if you're close to the surface of Earth, it might as well be an infinite plane for all you can tell. Same deal. For any surface charge, if you get close enough to it, it looks like an infinite plane because you're like, hey, infinite plane. Even if this were some big curved surface, I get close enough to it, it's like I'm looking at some infinite plane, locally
You
speaking.
should leave your glasses on.
I should just leave my glasses on, yeah. And then I'd just be like, yeah, I could probably survive, but all right. So is that happiness? That makes sense? Get close enough to any surface, it looks like an infinite plane, and so therefore that means that if I get close to a surface, then the local field due to the surface itself, due to the surface charge there, is going to be this. It's going to be sigma over 2 epsilon naught away from the surface. Due to the charge on the surface itself, get close enough to it, the surface itself, the surface charge sigma, is locally producing a field sigma over 2 epsilon naught away from the surface if sigma is positive or towards the surface if sigma is negative. The little unhappy step.
You just said it's sigma over 2 epsilon?
Yeah. Due to the patch itself, due to the charge on the surface itself, that's the field. But that's not the whole story, because the total field is due to all the charge in the system. The total field is due to all the charge in the system, including all the rest of the
I thought you
charge.
said it couldn't have an E going into it, so wasn't it?
Ah, see, see, this is the point. So consider a conductor here, all right? So,
Oh, we weren't considering a conductor there?
oh, we could be,
Okay.
right. Here, this is general. This is not a conductor
Yeah, okay,
necessarily.
That makes sense, I get
Right,
it.
this could be something else.
Mhm.
If we specifically go for a conductor, this is still last time stuff, okay? So, what happens? If I look at this little patch on the surface of the conductor, that patch itself is producing this field, sigma over 2 epsilon naught, up and down. Or if it's negatively charged, it'd be into it. If it's positively charged, both ways out of it, okay? But the total field, we know, is 0 below, sigma over epsilon naught above. So how can that be? What that must mean is that the rest of the charge on the conductor is contributing its own field such that it cancels the local field due to the patch inside the conductor and reinforces it, doubles it outside the conductor. So in other words, the argument we made last time was that at the surface of a conductor, the total field of sigma over epsilon naught n hat here and 0 down here is equal to the contribution due to the patch itself, sigma over 2 epsilon naught n hat over here, and minus sigma over 2 epsilon naught n hat down there. So here I'm taking n hat to be upwards out of the conductor. So this is part of the conductor's surface here. Okay, so patch plus other, all the other charge in the system must be contributing a field which is going to add to this and give sigma over epsilon naught n hat. So what do I add to sigma over 2 epsilon naught n hat to get sigma over epsilon naught n hat? Sigma over 2 epsilon naught, yeah, n hat. So the rest of the conductor is producing sigma over 2 epsilon naught n hat upwards. Above, what about below? What do I have to add to minus sigma over 2 epsilon naught n hat to get 0? Sigma over 2 epsilon naught n hat. Or in other words, the rest of the conductor in the vicinity of the patch on both sides, above and below, is contributing a field of sigma over 2 epsilon naught n hat. That adds to the field due to that local piece of charge itself, sigma. That adds to the field of sigma over 2 epsilon naught up and down to produce 0 inside the conductor, sigma over epsilon naught outside the conductor. Yes? Other means all the other charge in the system. Now, okay, so it's right. How big do I make my patch? Is that like, you're worried about
Are you
that?
just saying that those are those values because that's the way I'm talking?
Yeah. Uh-huh. See, the thing is that, remember that I can get, we're making, of course, charges really come in discrete packets. They're electrons or protons or whatever. But in the theory that we're developing here, if there really were a surface charge density, it wouldn't be little discrete point charges. Now, in reality, a surface charge is lots of closely spaced electrons or whatever, okay? But in the mathematical model we're making here, we really do pretend charge is a continuous quantity. So you really could have a sigma such that no matter how finely you divide the surface, there is charge in each little element of that surface. In reality, no, because it really, eventually you'd get down fine enough, you'd be seeing the individual electrons. But in our mathematical model, our sigma is really a continuous quantity. It really is a charge per unit area such that I can make the areas as small as I like. I don't care about the Planck length. I can get smaller than the Planck length in this model and look at little charge inside the something 1/1,000,000th the size of the Planck length. No, we can't really, but this is a model, you know, that we're making here. So, since I can get as close to the surface as I like, the little piece of patch I'm considering, no matter how tiny it is, looks like an infinite plane if I get close enough to it. So I'm really, you know, in the limit talking about at a point on the surface of the conductor with charge density sigma, if you like, the point itself has electric field associated with it of this and this, and the other is everything else. Everything else literally besides that one point. You can take that limit. Now, I haven't said that because of the fact that in reality you can't do that. So if you're going to do this in a practical terms, you might make, you know, like a 1 square micron area of the surface of the conductor. And other is everything outside that 1 square micron area. But it doesn't matter. You can make it half a square micron and other is everything outside of that. Because you can get as close to the surface as you like in the mathematical. Does that make sense? Okay? So that's the idea. So literally, mathematically, other means everything besides that point. All the charge on everything besides the one point on the surface of the conductor that we're talking about. Or in practical terms, you could back off a little and take a little tiny patch and others everything outside that little tiny patch that you're considering. But the size of the little tiny patch is kind of up to you as far as that's concerned. It just has to be, you just have to be close enough to the conductor that you can draw some little tiny patch, and that patch is going to look like an infinite plane to you. So there's some slipperiness into what you call other, but it's because it doesn't really matter. And mathematically, you can make it down to a single point that you're talking about. Okay? That's a good question, actually. It's bringing out a subtle point here. Okay? Other questions? Do we have more happiness than we had before? 4, yes, okay. So now we're back to the end of Tuesday, I think. All right, so, and now today, we're going to talk about, suppose in general you don't have just like a conductor. What if we're just talking about a general surface charge distribution? We're not going to assume it's a conductor anymore. Well, in that case, well, we'd like to figure out what is the force per unit. We're literally just doing it again, but that's okay. What's the force per unit area on a surface charge? Well, it's going to be, excuse me, since force is charge times electric field, remember, since force is charge times electric field, it'll be, you would think that charge per unit area times the electric field. So the force per unit area is the charge per unit area times, shoot, times the electric field at its location. But wait a minute. The electric field jumps at a surface charge. So what, Chad, if you really understood the last lecture, I should have said this, but you just fast forward to the last 10 minutes of the first part of this one here. Okay. No, but Chad finished the last DVD saying, what the hell was he talking about? And then I'll watch the first part of this one with it. Thank God, they finally asked that question, right? But, all right. But what electric field is it feeling? Because after all, the electric field jumps at the location of the surface. Well, you know what? It turns out it's the average of the electric field on the top of the bottom is what you should use for E when you're calculating the force on that charge. So, let's zoom in again on a little piece of surface charge, only this time we're not assuming that it's inside of a that it's at the surface of a conductor. So we're not allowed to assume anymore that the field is 0 on the bottom and sigma over epsilon naught on the top. Instead, we just say, in general, we still know that the patch is contributing sigma over 2 epsilon naught away from it in both directions, above and below, if it's positive charge, or towards it if it's negative charge, and we'll just draw it for positive charge. Now, for a conductor, we deduced that E other had to be sigma over 2 epsilon naught outwards. But if we're not in a conductor where we don't know that the field is 0 below the patch, then we just have to say E other is some general vector, whatever it might be. And so then we say, okay, the field above the patch will be the field due to all the other charges in the system plus the field of the patch itself. And the field below the patch will be the field due to all the other charges in the system plus the field of the patch itself, which is minus sigma over 2 epsilon naught n hat below the patch. Okay, but then I can just add these two things together and deduce that E above plus E below is equal to twice E other, or in other words, that E other is in fact, E other is in fact half of E above plus E below, which is the average of the electric field on the two sides of the surface. So if I know the electric field above and below some surface charge, I just average those two values, multiply it by sigma, and that will be the force per unit area on that surface charge. Okay? Have we achieved charge nirvana? Yes,
Just one
question.
stupid question. So are you saying like right before we had just said that E other was sigma over 2 epsilon naught and that pointing upwards in order to cancel out the E below?
This is for a
For a
conductor.
conductor. So this fits because it says E other equals 1/2 of E above and E below, which would be sigma over epsilon naught?
Yeah.
So it's, okay.
Right,
So
yeah,
so what you're saying is that-
so for a conductor, right, if we use this to calculate it for a conductor, you're absolutely right.
Okay.
For a conductor, we would say it's 1/2 of sigma over 2 epsilon naught n hat plus 0, which is equal to sigma over 2 epsilon naught n hat. So we would deduce for a conductor that E other must be sigma over 2 epsilon naught n hat based on this. And so it's perfectly consistent with what we said before. Only now we've made it more general because now we're not assuming anything about it being a conductor. This could just be a rubber sheet with charge on it. And there's something else over there. There's electric charges over there making an electric field. There's rubber charges on the sheet. And so the sheet itself has an electric field up away from the sheet. The other charges in the system produce an electric field. The electric field jumps at the location of the sheet. Why? Because the sheet itself is causing the jump. That's the other thing. The reason why the electric field jumps at a surface sheet, at a surface charge, is because of the sheet itself. It's the thing causing the jump. So for example, if I had a infinite sheet of charge, sigma, and over here I've got some point charge. The total electric field would be the field of the sheet plus the field of this point charge. And if this were a conductor, this wouldn't work because I couldn't assume constant sigma if it were a conductor because charge would flow in order to cancel electric field inside the conductor, etc. But if this is an insulator, charge can't move on it. I can distribute charge on it any way I darn well please. So here's this point charge sideways Q at the bottom. Here's the surface charge here. And so the field lines of sideways Q would just be the way they always look. But then you'd have to add to that the electric field of the sheet itself. So clearly there's no discontinuity in the field due to the point charge down here caused by the sheet because it's just the field of this point charge and it doesn't care about any other charges in the system. So if I considered a little patch on the sheet here and asked what's the force on that patch, the answer would be sigma times the field due to the point charge because that's what's going to exert the force on it. And so then you would say, okay, how could I figure that out or whatever if I just knew the value of the field above or below the sheet? Well, above the sheet it would be field of the point charge plus sigma over 2 epsilon naught this way, and below the sheet it would be field of the point charge plus sigma over 2 epsilon naught that way. And when you averaged them, those fields of the patches would cancel, and you just get the field of the point charge. E average would be the field of the point charge, which would be multiplied by sigma, and well, gee, that should be true, isn't it? Because it's the point charge which is producing the force on that, because the rest of the charges by symmetry aren't producing any force. Now you're looking at me like I'm crazy.
You're just talking
You
about.
just said it's.
Blah, 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 blah.
That's,
Right.
yeah, that's what it is.
Right. Was what I saying what I was saying making sense?
Yes.
Okay. So the discontinuity in the electric field at a surface charge is due to the patch, due to the surface charge itself. That's why there's that discontinuity. Why does it jump by sigma over epsilon naught? Because the field of the patch jumps by sigma over epsilon naught when you cross it. So the discontinuity is due to the patch itself, due to the surface charge itself. Due to the fact that the surface charge itself is sigma over 2 epsilon naught down on one side, sigma over 2 epsilon naught up on the other side, unless it's negative, but then that's no contradiction because minus up is down, so to speak. Happy you? Okay, you're welcome. So have we achieved greater happiness than we had before? All right. Then let's exercise our capacity for happiness by talking about, can you guess? If we're going to exercise our capacity for happiness, we must want to talk about capacitance, yes.
Yay.
Uh,
My favorite word ever.
capacitance. Yes, capacitance. All right. Though capacitors that are manufactured don't typically look like this, you could make a capacitor like this that just consisted of 2 conductors. And so we're going to put charge plus Q on one conductor, charge minus Q on the other conductor, and they're going to, because positive charges like negative charges, there's going to be a tendency for the charge to distribute itself so that there's extra charge density on the parts of the surfaces that are nearer one another, because that can get positive charges closer to negative charges. So you'll get something like that, where there's a buildup of extra charge density in the region where the conductors are closest to one another. And if you draw the field lines for this configuration, well, you can sketch them without knowing any great detail. Because what do we know about the electric field at the surface of a conductor? It is what to the surface? Perpendicular to the surface. So any field line you draw has to be perpendicular to the surfaces of both conductors. So in other words, if I draw the field line right here, it has to come off perpendicular, and it has to land perpendicular on the other side. So while that doesn't tell you everything you need to know, it tells you enough to at least sketch in a decent approximation to what the field lines ought to look like in the configuration. So I'm not claiming that this is necessarily accurate what I'm drawing here, but something like this is probably about right. And the field lines are they point from the plus to the minus or the minus to the plus? Plus to minus. Field lines point from plus to minus because a positive charge would feel a force in the direction of the field line, so therefore they point from plus to minus. So this contraption has an electric field, something like this. There's field lines over here too. They come way around and finally come back and land on the other one. And so there's going to be a potential difference between those conductors as a result of charging them up. And so we'll say that the voltage across the capacitor, the pair of conductors, will be potential of the positively charged conductor minus the potential of the negatively charged conductor, which of course is going to be minus the line integral from the negatively charged conductor to the positively charged conductor. So we'll just symbolize that by putting little parentheses with minus and plus in them, of E dot dl. Does it matter which point I pick on the conductors to do the line integral between? Nope. Line integral is independent of path, and so it doesn't matter which path I follow between the two conductors. Another way to say it is they're both equal potentials. They both have well-defined potentials, and so it should be true that I can take V plus minus V minus and not worry about which point I'm on the conductors because they are equal potentials. Each conductor has a fixed voltage, a fixed potential at each point on its surface. Now, an important point is that if we were to calculate the electric field, which in general would be like, you know, it's like, man, I don't even want to try. Throw a computer at it. But if we did, and we knew what the charge density was, well, we would just be doing our beloved integral of sigma dA for the little dq, right? dq is sigma dA r, script r hat over script r squared over 4 pi epsilon naught. Just integrate that over the charge distribution. So if this is my field point, I draw the little script r to each point on the surfaces of both conductors and integrate over the surfaces of both conductors of sigma dA r hat over sigma dA script r over hat over script r squared times 1 over 4 pi epsilon naught. It's just the integral of dq over 4 pi epsilon naught script r squared over the charge distribution. If we double sigma everywhere, which would thus double q, right? If I doubled sigma everywhere, that would double both plus q and minus q, so that the charge in the system would be doubled too. If we doubled sigma everywhere, what would that do to the electric field at each point in space? Hint, the only thing that changes is sigma becomes twice as big, so the electric field becomes twice as big. This would double the electric field everywhere. That would double E everywhere. And thus, double that line integral. That would double that line integral from one conductor to the other. So it would double the line integral, i.e. V would be doubled. V plus minus V minus equals V would be doubled. The potential difference between the two conductors would be doubled if you doubled the charges. Or in other words, it should be true that we can write that we can define some constant, C equals Q divided by V. This is just saying, in other words, if I double Q, I double V, so the ratio of Q to V must be some constant. And we call that constant C, and it goes by the name of capacitance. So the argument here is that even though it might be actually quite complicated to figure out what V was theoretically, you know, to say if I put plus Q and minus Q, you know, actually figuring out how the charges will distribute themselves and therefore produce an electric field and produce a voltage and so forth, at least we know that the voltage should be proportional to the charge, so that I can form their ratio, call it the capacitance, and the capacitance is only going to depend on the geometry, the shapes of the conductors, their sizes, how far apart they are, how they're oriented in space. C only depends on geometry. Actually, calculating C for a given configuration can be a nightmare But it only depends on the geometry. And of course, in practical terms, well, you just measure it. You know, you just put a charge on it and measure the voltage or whatever. You know, you measure the capacitance. Actually, that's not how you really do it typically. You put it in a circuit, like an AC circuit or something like that. But it's something that can be measured often much more easily than it can be calculated. Okay, go forth and lineify. Use my fancy remote here. All right. For you Winkies. Hello, Chad.
Zero carbs, zero calories.
Oh, what a Russian figure.
How much is in that? 230.
Debugs.
Well, if you're gonna drink it,
Well, no, I can multiple ones, that's the problem.
Man, I don't know how you.
There are 90 calories
Just
and
be like-
21 grams of carbohydrates.
But that's only one serving.
Really? Huh.
Yeah, and there's 2 servings for this, so 180.
Really?
Drinking 2 servings.
The average is 200 calories per drink.
I don't really drink caffeine.
So when you drink
Do I
like
need to worry about it?
That could be, I don't know.
Well, with that, the calories are all coming from the sugar, so it's it probably does something bad to you.
I think it would.
I mean, it may not make you overweight or anything, but I'm sure on the sugar, it's not good.
Okay, onward and upward here. So, let's do example 210, shall we?
Please.
All right. Happiness and joy comes from doing example 2.10, wherein you've probably done this before, but you may not remember it. The parallel plate capacitor, we calculated its capacitance, right? The old parallel plate capacitor. So that's where you have 2 parallel plates, hence the name. And so the idea here is there's a distance d between those plates, and each plate has area A, and one plate has charge plus Q, the other plate has charge minus Q. That's always true with a capacitor. I mean, you could make them different charges, but in practice, in a circuit with a capacitor, you're transferring charge from one plate to the other, so one gets plus Q, the other gets minus Q. All right, and so we want to know what's the capacitance of the parallel plate capacitor. So, well, first of all, the actual field is very difficult to calculate because of the fact that they are not infinite planes. But as long as they're large compared to their separation, you know, if d is smaller than the lengths of the plates, then lengths and widths of the plates, then you ought to be able to approximate it as 2 infinite plane charges. And so what would be the electric field if we kind of take a side view here? So here's the top plate, and here is the bottom plate. So the plus charges will mostly accumulate on the bottom surface of the top conductor, and negative charge will mostly accumulate on the top surface of the bottom conductor. What's going to be the field between the 2 plates? Well, yes, right, because, yeah, you know, think of this as an infinite sheet of charge, and it would produce sigma over 2 epsilon naught, sigma over 2 epsilon naught. Meanwhile, this one would produce, which way? Sigma over 2 epsilon naught, sigma over 2 epsilon naught. So the fields cancel above and below, because if they were infinite planes, this one would have sigma over 2 epsilon naught above, this one would have sigma over 2 epsilon naught in the other direction above, like this. So those would cancel down here. We go like that, and so they would cancel again, whereas in the middle, they're both pointing downwards, reinforcing both sigma over 2 epsilon naught. So to a good approximation, the electric field in between the plates is just sigma over epsilon naught pointing downwards for the electric field. And roughly 0 outside. Not exactly true, but we'll just use that approximation. And that means that the voltage, the potential difference would be what in that case? Well, if the, looking at me funny, if the,
Give me a look.
yeah,
Sorry.
I'm just expecting to hear something about
I'm sure it's on tape, actually.
Rufus Grin, whatever his name is, not him. Rupert Grin, right? Oh, no, that's the guy who plays the guy, right? I can't, yeah, that's right, yeah. I'm thinking of the actual actor's name. Because last time was Hermione, you know, so.
So wait, what else?
Harry Potter?
Well, last time it was Hermione, some silliness about Hermione Granger, so. Right. So anyway, so what's the voltage, right? Well, if we're gonna take that line integral and the electric field's just down everywhere, we can just traipse between them, right? Yeah, traipse from the -1 to the +1. And so, in other words, if in this case, the voltage is just the electric field times the displacement d, right? The field is always along the direction that you're doing the line integral, then the line integral just works into electric field times d, because the electric field is constant here. So V is equal to E times D, but that is going to be equal to sigma over epsilon times D, but sigma is just going to be Q over A. If we just assume that the charge distributes itself uniformly, sigma is going to be Q over A, so this will be Q over A epsilon naught times D. So then the capacitance, which is equal to charge divided by voltage, is just A epsilon naught divided by D. Ta-da, that's it. So it's quite easy to calculate V for this simple, C for this simple geometry. The capacitance is just A epsilon naught over D, and if the plates were, say, 1 centimeter by 1 centimeter, and D was a millimeter, then we get, put it in using epsilon naught and so forth, about 9 times 10 to the minus 13th power farads. And I forgot to mention, by the way, units for capacitance, since it's charge over voltage, is going to be coulombs per volt, and a coulomb per volt is called a farad. So the capacitance of a parallel plate capacitor, 1 centimeter by 1 centimeter with a millimeter apart separation of plates, would be 9 times 10 to the minus 13 farads, coulombs per volt, which just goes to show you that a farad is a big amount of capacitance, basically. You know, in circuits, capacitors that you use are typically will have capacitances on the order of some number of microfarads or picofarads. And, you know, here we're talking about, what's that, 10 to the minus 12 farads is a picofarad, so, what's that?
0.9 pico.
Yeah, so this is 0.9 picofarads here, right? So, and there's an interesting thing I noted in the book, that in the previous edition, your book's from 1999, and he says in this previous edition, he said that a farad capacitor would be, you know, a kiloohm or something like that. I forget what he said, but it is actually possible now to buy farad capacitors that you can hold in your hand. And that's because they've got a good, strong dielectric in them. Later we'll talk about dielectrics, which you may recall, you must have in 111 talked about dielectrics and how you increase capacitance and so forth. So we'll get to that later. But for now, we've just got a vacuum capacitor, and boy, it's digital. If you wanted a farad capacitor with a parallel plate capacitor and a vacuum, it would be a big mama, basically, is what it comes down to. Example 2.11. Let's do a slightly more complicated geometry. Namely, let's have two spherical, a spherical shell surrounding a spherical conductor. And we ask, what is its capacitance? We also ask how we can manage this. Of course, there has to be some insulating strut between them in order to, you know, make this work. But the idea here is that if this has radius A and this has radius B, I guess it's actually supposed to be two spherical shells, but it doesn't matter. The inner one could just be a solid sphere. Yes?
So what's going on in this picture?
So this is, what this is supposed to represent is, here's a sphere, and here's a hollow sphere surrounding the inner sphere. So this is vacuum in here.
Oh,
This is metal. Well, this is a spherical shell of metal
with a certain.
with a sphere inside of it.
Well, with a significant distance.
Yeah, right. Well, it could
It's
be
not-
anything. Yeah, but in other words, B minus A is the distance between the conductors.
Which are both the outside circles make up the shell.
Yeah,
That's
right.
right.
So right, this is right.
That
Yeah.
was thrown.
Right, yeah, sorry, this is a shell, so in other words, there's metal in between here, that's the point. I mean, I could have just drawn it
It's
as
not
a circle.
arbitrary.
It's what?
It's not like infinitesimally small. Like it's-
It could be, but you know, it doesn't matter, because all the charge is gonna go to the inside surface anyway, so. So the idea then is, let's go ahead and put minus Q on the outer spherical shell conductor, and we'll put plus Q on the inner spherical conductor. And the charge will arrange itself so that the plus Q is uniformly distributed around the inner conductor surface, and the minus Q is uniformly distributed around the outer conductor's inner surface there, just by symmetry. You know, how else could it be? This is a spherically symmetric system, so how else could it be, really? And so the electric field is then going to, in this case, be looking like this. Here's field lines. They'll just be pointing radially out from the positively charged inner sphere to the negatively charged outer sphere, like that. And so what we have here is going to be what? If I've got a spherical shell of uniformly distributed charge, its field looks exactly like the field of a, at the origin, right, or the center of it, yeah. So the electric field, in other words, in between the two conductors is just Q over 4 pi epsilon naught r squared times r hat, where we pick the origin to be at the center of the inner spherical conductor, or the center of this whole contraption here. That's just the electric field there. And then it would cancel outside, notice, because the minus Q shell would produce equal and opposite field. So outside there's no field. And again, in the next chapter we'll prove a uniqueness theorem, which says basically that if you can meet the boundary conditions with a guess, it's the only possibility, and that'll clarify what that means. You keep looking for money when I say that, but it'll make sense when we get to that. So this is what the field looks like, and so now we have to integrate the electric field in order to find the potential difference. So we want to go from B to A, minus the integral from B to A, because we're supposed to go from the negative one to the positive one. So B to A of E dot dl. Well, I'm going to flip it around and make it plus the integral from A to B of E dot dl. I can always flip the limits and change the sign. And then that says go from A to B of Q over 4 pi epsilon naught r squared r hat dotted into, if I choose, I can simply follow a field line out. I don't have to, I can take an arbitrary path, but why do that when there's a very simple one that just follows the field line? So let's just integrate along the field line, in which case dl is just dr r hat, just a little displacement dr in the r hat direction. And so that means that we're integrating Q over 4 pi epsilon naught times the integral from A to B of dr over r squared, because the r hat is 1. And that's an integral that you can do. You just put that into Mathematica, and then I slap you for it. That's equal to Q over 4 pi epsilon naught times turns into minus 1 over r, and then when you put it, so it'd be minus 1 over b minus minus 1 over a, so just flip it around. 1 over a minus 1 over b, and then the limits. Okay, so everybody on board so far? Happiness, joy, all right. So that's the potential difference. And then the capacitance, we always just get from Q divided by V. So if I divide Q by V, that's going to give me, well, the Q cancels, as it always must. You always have to find that the voltage is proportional to Q. And so Q divided by V, you're going to get 4 pi epsilon naught over 1 over A minus 1 over B. But then what you do is just multiply top and bottom by AB, and it simplifies to 4 pi epsilon naught times AB divided by B minus A. For the capacitance of our spherical shells like that. Okay. What's that? For 111. Oh, really? Oh, yeah? You were supposed to memorize that? No. Oh, just know it. Really? Really? Huh? Did you derive it, or did you just say that's the answer?
You derived it in a book.
Yeah. Oh, okay. Well, now we just derived it. You're certainly derived in your book. I just took this from the book, basically. So.
For example, 2.11.
From example 2.11. That's right. Yes. Yes,
Wow.
that's right. Very insightful.
You know, I was looking in the book and following along.
Yeah. You got to get up pretty early in the morning to
What?
to pull one over step size.
I.
All right. So, of course, you can make nice cylindrical capacitors, and then you end up getting natural logarithms out when you find the capacitance, because then you're integrating dr over r instead of dr over r squared. But that's enough of that. Finally, we ask ourselves, how much energy is stored in a charged capacitor? I've amused myself before by taking LED watches that were broken and connecting them to the terminals of a capacitor. And boy, they can run for many, many hours just from the capacitor slowly discharging, because they have such a high impedance that the capacitor is practically a battery for those things. So anyway.
You just use yourself for
Side
hours.
note.
Well, I would say, I just sat there, right? Yeah, just stared at the display. Just as it kept moving forward.
That
So when did you do this?
When I was in high school.
So it's confirmed.
Oh.
Yeah, yeah.
Aw.
It's gonna have ice.
Well, yeah,
high school nerd.
that's right, yes. But I
Is
was
that
also-
when you decided you wanted to become an astronaut?
Oh, no, that was when I was like 6 or 7 years old. My dad showed me a painting of the solar system. Yeah.
Just a painful.
Well, yeah, it was a painting of the sun and planets to scale, and I, he asked me to point to the Earth, and I could see for myself that Earth was much bigger than any of those little lights in the sky. So I pointed to the biggest thing on there, and he said, "That's actually the sun." And my jaw dropped. So then he said, "Try again." So I said, "Well, obviously it's this one." He said, "That's actually Jupiter." So my jaw dropped again. So he said, "Try again." And I said, "I give up, Daddy." And he pointed to the little blue dot, and I was hooked. At that moment, I had my epiphany, like, I have to know everything about that. So, yeah.
I'm gonna try this.
So I was like, when I was in 2nd grade, I was like writing little books about the solar system and stuff.
I remember this.
I'm gonna try and inspire my children and be like, look at this picture of the
The
solar
solar
system.
That's right,
Which one's the
yes.
Earth?
Which one's the Earth? They're gonna be like, it's this one. And I'm gonna be like, dang it.
The problem is you're gonna have that label,
Here's
the
part of
picture of the
it.
solar system.
Earth. Which one is Earth? By then it'll just be us.
Right.
Just be honest. We're just gonna destroy all the other planets. Don't worry.
Whereas there's an episode of The View with their new co-host, This
who's the
woman,
new
like,
co-host?
oh, it's like Sherry Ferguson or something like that. Sherry Simpson, something like that. Anyway, she starts talking about how she doesn't believe in evolution.
Really?
And Whoopi Goldberg says, to much to her credit, Whoopi Goldberg asked her, he says, do you believe that the earth is flat? And this woman, in all seriousness, says, I've never really thought about that. She didn't know for sure whether the earth was flat or not.
Kathy
She wasn't
Griffin.
kidding. No, it wasn't Kathy Griffin.
Oh,
No,
good.
she didn't do that. No.
I've never really thought about it
And you
before.
can, yes, the clip is on YouTube, so you can find it actually.
I've never really
Yes.
thought about it before.
Yeah.
Sherry
Well, it's
Shepherd?
fine. Sherry Shepherd, that's the one.
Oh my
yes.
gosh. Get a picture of
It's a
it.
mind
I'm
blower.
trying.
Copy the name and Google image.
I'm getting it blonde.
Right, so I was thanking Whoopi
Whoa,
Goldberg
that
for
is not
pointing that out. Yeah.
Sherry Shepherd.
Oh,
It just brought up a MySpace awkwardness.
Oh, okay.
Maybe she has a MySpace. What?
It was, but she was awkward. She kind of looks like Star. Whoa, referral denied. That's Sherry. Awkward.
Oh, Lord.
Is this Sherry?
Are you judging off?
That's her. Yeah.
She looks like Star.
Star Jones, the co-host who was like kicked off.
Sorry.
Hold on, I'll show you.
I never really thought about these things.
Well, now
It's
she's
a show
speaking. I'll
on
show you a
ABC
picture of her.
Camera.
Actually, this is
It
a
always
picture of
comes on
Star.
after.
That's a
every
picture of Star Jones. Can you see now?
Nope.
They do look like the same person, but that's a
Yeah.
very small picture, so it's very small stuff.
Hold on.
Oh, that's kind of
I know, I'm just up here. Right?
Stop distracting.
He's the one who started it.
This is true, Doctor.
So anyway, consider transferring dq from the minus plate to the plus plate when their charges are plus and minus q at some moment, right? So here's my cute little picture, plus q minus q, whee, dq goes around from the negative plate to the positive plate. Of course, in real circuits, electrons are what is flowing, but we always pretend that positive charge is flowing in our circuits instead of negative charge. But that's okay. So, little charge plus dq goes from the negative plate to the positive plate, and that takes some work because you're forcing it to join those positive charges, and positive charges are like out of my face under positive charges. And so, so the voltage at that time is Q over C, and so therefore the work that takes is the voltage times the charge, Q over C dQ, right? So each little chunk of charge takes Q over C dQ to move from one plate to the other. And so therefore the total work is just you add up all the little work that you did to transfer each chunk of charge from one plate to the other. So you add up all the little dW's. Or in other words, you integrate from 0 up to the final charge of Q over C dQ, which, well, that's not a tough integral to do. That's another one where you put it into mathematics and then I slap you silly. Q squared over 2C, right? Yeah, and by the way, when you're doing Mathematica stuff, if it's something you could do by substitution, I'm not going to be pleased if you did it with Mathematica. So do look for, at least, if you do an integration by substitution, don't let Mathematica do the integral for you, because then you're just being, lazy or whatever. So if it's some weirdo, some weirdo thing.
What about being efficient?
Huh?
What about being efficient and giving us more points for it?
No, don't be silly.
What about precise?
Precise.
Mathematics is precise.
I see, yes.
I mean, I don't like to make mistakes.
So Q squared over 2C, whether you just check yourself and you pretend you didn't. I'm all for checking yourself and then.
I'm going to turn all my homework problems on my sheet paper, so that I checked them, and according to me, they weren't wrong.
They were wrong there. There you go, right.
Really good at substitution in my head.
What's that?
I'm not really good at doing substitution in my head. Just write down the
Well, yeah, no, you should show the substitution, right, yes. Now, of course, if it's something you'd have to do by partial fractions or something like that, well, that's just like mathematically. Because honestly, I actually don't, off the top of my head, I can't do partial. I don't remember how to do partial fractions.
Partial fraction.
Yeah, I did, but it's one of those things I need every couple of years, and with mathematics, I never need it, to be honest, so. Yeah, right. It's like every once in a while I know how to use a slide rule because I'll get interested and teach myself and then I forget again. So anyway, half CV squared if you just use the fact that Q is equal to CV and plug in, you get CV squared over 2C. Half CV squared, boy, I'm sure you remember those formulas, right? Energy in a capacitor is half CV squared or Q squared over 2C. From those halcyon days of 111, you remember those little snippets. Halcyon. Halcyon. Yes. Right. Yeah, that. Right.
What? I don't get it. I don't.
Those wonderful days of 111.
Those lower halcyon. Yeah, I don't get the halcyon part.
You don't?
No.
Doesn't halcyon mean like wonderful, terrific?
It's an actual word?
Actually, I think it means peaceful.
Oh.
Peaceful? I'm not sure, actually.
I thought we were.
I will let you
But they
know.
would be peaceful and
I
wonderful.
thought we were taking the time.
Actually erase that when you tape, because then I'll feel silly if it turns out it's.
You got something.
It's like terrible.
Right, yes.
Yeah, you're right.
Okay, you know what it means?
Yeah.
It's there's several different, a kingfisher, a fabled bird, calm and peaceful, tranquil.
Calm and peaceful and
Prosperous,
tranquil.
golden.
Prosperous and golden, that's the context I was with. That's the meaning I was
Halcyon
with.
years.
Yes, exactly.
Yeah.
Prosperous,
I thought you meant
golden, kingfisher, yes. That's
It's especially one of the genus Halcyon. It's actually a genus.
Oh, there you go.
One of those things I never learned.
Or, how do you say it, G-N-U-S, is that genus?
Apparently I said
Genius?
guillotine yesterday.
Guillotine?
It's guillotine. Yes.
I don't know
Chapter
what
3,
it is.
special techniques. We'll begin with, yes.
What happened to page 6?
It doesn't exist because I want to start chapters on odd numbers, so there is no page 60.
I can reflect.
Yeah, so 60 is blank, and then, that's right, yeah, so insert blank page here. I actually considered
For
writing
notes.
60 on the top of a blank page and scanning it in, and then I decided
That way you
against
would have
it.
never had that question.
That's true, that's
It's for
true.
your own note taking.
Yes.
I just didn't know if like
That would have been
maybe,
wasteful paper.
That's how I
You
felt
better.
about it, that's exactly right, yes. So,
What I like-
Laplace's and Poisson's equations. Poisson, yes. Simeon Denis Poisson. I've never had French, but lovely cake has.
did she tell you that that's correctly?
No, but it should be that, right? These are just Gauss's law written in terms of the potential. That's all they are. They're just Gauss's law written in terms of the potential, and Laplace's equation is Poisson's equation when there's no charge around. So, in particular, Gauss's law, yeah, that's a good way to get your name, yes. They- I know.
Oh, that's my law.
That's my law, that's right, yes.
You know, rearrange this, not law.
Yeah.
Basic law.
Yes, yeah. I've decided that maybe if the charge density is equal to 3 coulombs per cubic meter, then that becomes Harmon's law, that the divergence of V is 3 over epsilon naught in MKS units.
MKS.
MKS.
Like the.
Meters, kilograms, seconds. Okay, so, Gauss's law, is div E equal, the differential form of Gauss's law is div E is equal to rho over epsilon naught.
Just whole formulation.
I would not
Like
be-
that form.
We'd probably
Yeah.
get through 10 minutes of an actual discussion because I'd just see myself.
I was so laughing like that.
Yeah.
You had to.
Yeah.
From the sentence.
Since E is equal to minus grad V, then in terms of the potential, what we have would be that we could say that the divergence of minus grad
I don't want
V.
someone to walk in.
Oh my
I
god.
missed all of that.
I'm so glad I just went to the bathroom.
Yeah. Hi, dear. If you didn't think I was insane before,
Perfect.
What were you doing?
I was just using the differential form of Gauss's law. So I have to speak in high voice. Oh my God. Or, since we call the divergence of the gradient the Laplacian, grad squared V is equal to minus rho over epsilon naught. In terms of the potential, that's what Gauss's law looks like. Grad squared V is minus rho over epsilon naught. And that goes by the name of Poisson's equation.
Poison's law?
Yeah, Poisson's law, that's right. That's Poisson's equation. After good old. So, lovely wife, you can critique my attempted pronunciation here. Simeon, Denis, Poisson.
Good enough.
Good enough.
Say it, say it.
Yeah.
I don't, well, other people speak French in here, right? Anyone taking French?
No.
Well, I haven't taken French in a long time, but it should be Simeon Denis Poisson.
Okay. Not too bad. Bad for a duffer.
Well, your German is good.
Yeah, that's right. Yeah.
Do it.
I'm scared.
In the
Seriously, real German speakers,
It's right.
it scares
It
me.
is, yeah.
It scares me. I'm like, you need to stop. Like, because they're so like, it's such a like a volatile language.
I want to speak it.
I know. I am German.
Okay.
Therefore, I'm volatile.
That guy, if you listen to the German professor, if you listen to German professors speak, it's not that bad.
Well,
That's
but
They
they're
aren't
kind
screaming
of.
at you every time.
No, they're not. It's not like you need a spit shield or anything.
Well, like my family, we go to like Oktoberfest, and then you see like the cute little old ladies speaking German. They're volatile. They're not scary. But I don't know.
So set the charge equal to 0, and you get a whole new equation out.
You know what?
If I said it equal to
How
one,
does
can I make it
it
bigger?
seriously on that? Like, how staggers equal?
Did you just write it?
Yeah.
Did you just write it?
I look for something to zero.
Well, actually, I
That's
think
just
this
mine.
came first, and then Poisson, no, it's just historical, Plus, the thing is that this equation shows up in many contexts, not just in E and M. And so, he gets this equation because,
I'm starting to
Wasn't he a mathematician?
what's that?
Wasn't he like a mathematician?
Yeah, he was. Yeah, Laplace was in that. It made him, yeah, right. And he also made important contributions to celestial mechanics, perturbation theory, and so forth. Yeah. Yes, he was quite a genius in that regard. Maybe not as big as Gauss. Gauss was a genius. He really was. Yeah, he was a mathematical genius.
Do I think it's a thing like that?
Okay, now,
Yeah, see, clearly
I
has
point
to be
out,
the same thing.
this here is a magnificent equation because solutions to it are called harmonic functions. Oh yeah, right there. Harmonic functions are the solutions to Laplace's equation. Why? if I take any point and I put a sphere surrounding that point of any radius whatsoever, then if I average the solution over the surface of the sphere, that's equal to the value at the center of the sphere. A remarkable property. The average of a solution of Laplace's equation over a sphere, over a spherical surface, we'll say, is equal to the value at the center. Pretty remarkable. And we'll show that just by saying, well, we know that the electric field of a point charge satisfies Laplace's equation outside the charge, because the charge density is 0 there. And we'll just show that the field of a point charge, the potential due to a point charge, has this property. And then by superposition, any electrostatic field will have the same property, because you just add up the fields of all the point charges, and each one of them has that property that a whole distribution does. Corollary. There are no local, I haven't misprinted my notes, by the way, I'm going to fix it, repost it, but there are no local, I think I said no, what did I say, something?
No longer.
No longer, yeah. There are no longer, there are no local minima or maxima of the solutions. If V is the solution, it has no local minima or maxima, and that's pretty easy to see because suppose some point was a local maximum, let's say. Well, if this is a local maximum, if I draw some small sphere around it, by the definition of a local maximum, it would be bigger than the value on every point on the surface of the sphere, but then that couldn't possibly be true that the average over the sphere was equal to the value at the center if the value at the center was bigger than every point on the surface of the sphere. That'd be like saying, you know, that I'm the oldest person in this room, let's say, and then the average of all your ages, you know, is equal to my age, and well, if you're all younger than me, well, that's not going to work. You know, it can't happen. So if it's true that the average over any sphere is equal to the value at the center, it can't possibly be true that the center is a maximum or a minimum, because the average has to be somewhere in the middle of the range of values. So that means that any maxima or minima have to be on the boundaries. Any maxima or minima of V have to be on the boundaries because, you know, if I'm in a boundary surface, Laplace's equation only holds where there's no charge density. So if I'm on a boundary surface, I can no longer draw a sphere where Laplace's equation holds everywhere on the surface of the sphere if I'm at a boundary surface. And so this breaks down at boundary surfaces. So extrema of V can only occur on boundaries. The boundaries of the region where Laplace's equation is satisfied. That last point makes sense. If I'm on a boundary, this breaks down because on a boundary, like suppose that, you know, for example, conductors. So suppose I've got some region and I've got, here's two conductors. Here's an outer conductor and an inner conductor, and there's no charge in the region between the conductors. Then Laplace's equation is satisfied in the region between the conductors. But the conductors themselves might have charge on their surfaces. And so the surfaces of the conductors are places where Laplace's equation doesn't hold because rho isn't 0 on the surface of the conductor. So therefore, on a point on the surface of the conductor, I can't draw a sphere where Laplace's equation holds everyone in that sphere. So I can no longer make this argument. So on the boundaries, there could be extrema. Yes?
You draw a Cookie Monster.
I draw a Cookie Monster?
Yeah, little eyes up there, like little mouth.
Like, oh, here? Is this thing you mean? This is Cookie Monster?
Something like it, with the stars.
A very demented Cookie Monster. Yeah, it's like, yeah,
He's anti-Cookie Monster.
right. Yeah. Right. That's Cookie Monster after he took the wrong person's.
Oh!
I cut you, man.
Oh my gosh.
All right. So next time we'll prove this. We'll prove that it's actually true that its average over any sphere is equal to its value at the center. And then we'll prove some other uniqueness theorems where it'll finally clarify this issue of, I've kind of been waving my hand saying, if you can find a solution, it must be the solution, and I'll make it more clear what exactly that means. That precisely you have to satisfy boundary conditions or know the charges on the conductors, and then that makes the solution unique. Okay, bye-bye.